So today we're going to continue with chapter 1, Introduction and Motivation. So let me power up the slides. Right, so here we are with a brief recap of what we talked about last time. Namely, we talked about what I like to call the virtues of computer science. Um, First, precise, unambiguous problem specification before even starting to think about its algorithmic solution. Then fix the semantics of the operations that we are allowed to use. I'm going to illustrate that in particular detail in today's lecture. Then design algorithms rather than start coding, programming, analyze the algorithms with respect to their correctness and their computational cost, their performance asymptotically, and finally prove that the algorithm we have devised and analyzed is actually optimal asymptotically, and only then start optimizing the implementation, because as Donald Knuth pointed out, premature optimization is the root of all evil. And to illustrate the importance of problem specification, we considered several problems. To illustrate the point of semantics, that will be a major point in today's lecture. Um, the difference between algorithms and programs has been illustrated here on this slide. And we'll say more about the difference between algorithm and heuristic later. We have talked about pseudocode as one way of describing algorithms. Kind of blend between program and algorithm is pseudocode. There are many other ways of describing algorithm in a high level. And yeah, today I want to say a little bit more about the importance of assigning costs and choosing semantics of operations that we're allowed to use. So let us resume last lectures here at this point, with an example problem of multiplying two integers, let's say two integers that have, yeah, let's say n-bit integers. And so how would you design an algorithm to multiply two n-bit integers? What you probably have learned and seen in school, um, this is usually called long multiplication. You know long multiplication, and so how does long multiplication work? Long multiplication proceeds by writing the two integers in this way. Let's call the first integer a, and let's call the second integer b, and let's write b in its binary expansion indicated here. So this is to be understood as binary binary code. So, and the way of multiplying a to b is by considering kind of shifts of a. So this is the way we learn it in Germany. Maybe in Korea there's a slightly different notation. So we write down different shifts of a, moving a gradually one digit to the right, and then adding all these shifts of A, uh, um, yeah, taking the sum of all the shifts of A. Well, not all of them, because of course we're only going to take those shifts of A that correspond to position in the second argument B, where the corresponding digit is a 1. So if the first digit here is a 0, then we don't add up this shift of A. If it is a bit 1, then we do add it up. And so similarly, if the second bit is 1, then we do add A, the shifted version of A, and otherwise we don't. So this is the uh, probably what you know as long multiplication and so on up to the last digit of B. So the digits of B determine which shifts of A we keep and we sum, and which shifts of A we don't keep and which we thus don't sum up. So um, I guess this is what you know as long multiplication, a way of multiplying two integers. And now let's analyze this, uh, regard this as an algorithm and analyze it. And particularly we want to analyze it with respect to the semantics. Which operations does our long multiplication algorithm employ? And what computational cost do these operations incur, or what computational costs do we assign to these operations? That's the important question. We design costs to these operations, and the cost we design to them, that gives rise to the computational cost of the algorithm. And um, of course, we want to design realistic costs so that the overall cost that we determine for the algorithm um, actually um, uh, corresponds to and gives a realistic estimate of the um, overall cost and prediction of the algorithmic performance. So um, right, so the algorithm basically boils down to two operations, namely one is addition, summing up all these instances of shifted versions of A. So this is addition, additions of non-negative integers, integers of length 2n bits at most, because we shift A by at most n bits, and A is itself n bits long. So the different shifted versions all fit into one integer of length 2 times n. And so the algorithm can be described as adding up to n integers, each having length 2 times n, and which integers we add is determined by the bits of the second argument b, whether these are zeros or not. So another operation that is implicitly employed in this algorithm is testing a bit here of the second argument b. So, and from this perspective, this algorithm uh, incurs up to n additions of integers of length 2 times n at most, so that this would be considered as a linear time algorithm, right? A linear time algorithm employing the primitive operations adding n-bit integers, and the semantics of this operation is just our usual semantics of integer addition. And the cost of each operation here, we count the number of operations, we count the number of additions, so that the cost here with this cost measure, the overall cost of this long multiplication algorithm would be linear. Okay, so that's our first simple algorithm from, from school, long multiplication, analyzed and uh, agreed and being explicit about which operations we use and what cost we charge to these operations. Namely, the operations are testing bits and adding integers, and the cost is one charge for each operation. Now recall that the purpose of designing and assigning semantics and cost is to get a realistic estimate and prediction of the actual performance of the algorithm. And it seems that arguably assigning one charge, one operation, one step for each addition is unrealistic in that adding two integers which are long takes more time than adding two integers which are short. So a more realistic uh, uh, assessment and prediction of the performance seems to arise from if we do not assign what is called unit cost to each operation, but a measure of cost that depends on the size, on the length of the operations under consideration. Okay, and let's now reanalyze the same algorithm, but with different basic operations, not integer additions, but bit operations. So same algorithm, basically, but with different semantics, with different operations and different cost, with the purpose of getting a more realistic prediction of the algorithmic performance. And to this end, we switch from considering integers to considering bits. So now we also expand the first argument, a, into its binary expansion like this here. And instead of the shifted integers, we consider now shifted versions of this binary, finite binary strings, as you can see here. Okay. And now let's reanalyze basically, yeah, to be fully correct, this is now a different algorithm. It is still commonly called long multiplication, but technically it's a different algorithm because now it uses different operational primitives, not addition of entire integers anymore, but only operations on single bits, um, which makes it a more complicated algorithm, but the prediction of performance will turn out to be more realistic and more in agreement with what we experience when implementing that algorithm. And you recall that's the whole purpose of designing and analyzing algorithm to get a, a prediction of the performance of the implementation of the program before even implementing and running the program. Yeah, prediction is the keyword here. Good, so now we have long multiplication, and to be fair, this is probably the way you actually perform long multiplication. For example, of long integers, you write both of them in, yeah, in school probably in decimal. Here we do it in binary because we're computer scientists after all. And now observe, yes, as I said, the additions now um, involve uh, integers of length at most 2 times n each. And so we still have to add all these, or those which correspond to uh, non-zero bits here in the second argument. But now we charge to each operation, to each addition operation, not one step, but 2 times n steps, namely adding two integers of length 2 times n, obviously uh, can be expressed as 2 times or O of n operations on single bits. And now suddenly, with this new kind of primitives operating on bits rather than on entire integers, operating on single bits rather than on entire integers, now suddenly long multiplication incurs a cost of quadratic n times n, right? Roughly 2 times n for each addition, and again, still we have n additions. So the difference between the two algorithms and the difference between the two is the difference between the operations that we are allowed to use as primitives and the costs we charge to each operation. In the first case, the operations are additions of integers, and one step is counted for each addition. In the second perspective, we don't allow addition of entire integers, but only operations on single bits. Um, yeah, like adding with carry, and we charge one operation, one charge for each bit operation. And in the first case, that algorithm incurs a cost which is linear O of n. And in the second case, the algorithm incurs a cost which is quadratic. And my question to you is, which of the two perspectives of longer multiplication is more realistic? Which one gives the more uh, accurate prediction of the actual performance of long multiplication? Let's take a 1 minute break so that you can answer, think about that, that's a more important thing, and answer that question in the chat. Okay, time is up. So yeah, the answer is that the second perspective of long multiplication gives a more realistic prediction, because uh, the, when when implementing that algorithm on an actual computer, of course, the computer itself does not perform additions of integers as primitives, but has to break down integer addition into a sequence of bit operations. And so the bit operations, counting bit operation, gives a more realistic performance of, uh, of the algorithm when implementing it. And therefore, the second perspective is more realistic. But the first perspective is also permitted in the realm of theoretical computer science. Notice that the difference between both perspectives is that most polynomial difference. So when we're uh, designing and analyzing algorithms and investigating whether it's a polynomial time algorithm or not, then this difference can be neglected. But if we look more closely, then just polynomial, but we want to know which polynomial degree, then the second perspective is the preferred one. And in the sequel of this course, we will always take care to indicate which operational primitives are allowed, what is their semantics, and what is the computational cost of each such primitive. Um, and the reason is demonstrated here on this slide. Okay, so that being said, um, let's move on to the next slide. Right, so the difference between the two perspectives of multi-integer long multiplication is that in the first case, we consider additions as permitted operations with their semantics. And in the second case, we consider operations and on bits with their semantics. and as permitted operations. And so, in the second, more realistic perspective, long multiplication turns out to be a quadratic time algorithm. In the first, it turns out to be a linear time algorithm. But since the second one is more realistic, the question arises. Remember, that's the fifth virtue of computer science, whether this is actually optimal. Is quadratic time optimal? Um, and the answer is negative. No, it's not. And people have designed actually a sequence of better and better, more efficient algorithms for multiplying two n-bit integers, more efficient in terms of the bit cost, the second perspective. And the current world record actually has been achieved in uh, December 2020 by Harvey and van der Hoeven, who designed and analyzed an algorithm for multiplying two n-bit integers that use asymptotically n log n bit operations, n log n operations on bits. And recall, keep emphasizing this counting operations on bits gives the most realistic um, prediction of actual performance. So we're far from uh, presenting that famous algorithm of Harvey and van der Hoeven here, but we will present some algorithms for uh, polynomial multiplication that give you an impression of the kind of techniques uh, well used by Harvey and van der Hoeven. Okay, so that being said, um, right, we've emphasized the importance of asymptotic performance and recalled uh, classes of asymptotic rows, Landauer's big O notation. And so today we want to um, start considering um, three more example problems. The first example problems was the multiplication of two n-bit integers, and that was kind of the zeros problem. The first problem we want to consider is the problem of powering. So let's follow our virtues, our paradigm of first unambiguously specifying the powering problem and agreeing on which operation we allow for designing algorithm for the powering problem. So the problem is specified as follows. So we have some monoid. For those of you to recall, what is a monoid? A monoid is a mathematical structure which allows for multiplication. So many mathematical structures are monoids. For example, integers can be multiplied, real numbers can be multiplied, matrices can be multiplied, everything that can be multiplied associatively. That's important. Uh, Multiplication that uh, satisfies the associative law, then it's on a monoid. And interestingly, the integers are also monoid with respect to addition. So if you consider addition as the operation, that's also associative. So, but we're taking here the abstract perspective, the general perspective, considering uh, a monoid as a set together with an associative multiplication operation. And another input is a natural number n, and the goal is to output x raised to the nth power, that is, x multiplied to itself n times, x times x times x. So x to the n here is an abbreviation for x times x times x times x repeatedly n times. So that's a problem specification. Well, the first part and the second part of the problem specification is which operations are we allowed to use? And the answer is obvious here, but let's be very explicit so that you train uh, being explicit and following the virtues of computer science, namely the operation permitted here is obviously multiplication. I emphasize that because It means that exponentiation is not a permitted property uh, in this perspective. Um, we can also consider the powering problem when permitting exponentiation, but then the problem becomes kind of trivial, right? Then we just invoke the exponentiation operation and get the result x to the n in one single step, um, which which is yeah, not very interesting, and also the um, raises the practical question: how would one actually implement the exponentiation operation? And this is the question we are approaching here, namely how to express the exponentiation operation, integer exponentiation, using repeated multiplication. And we kind of defer and ignore the question how in turn to implement the multiplication operation, which, as illustrated on the previous slide, is itself a problem: how to express multiplication using more basic primitives, using, for example, addition, or using bit operations. So here the specification says uh, we are allowed to use multiplications and only multiplication, no division, no exponentiation, and we charge one multiplication, one as one charge, one cost, one operation, regardless of the size of the quantities to be multiplied. That's what we agree here. And then the problem is fully specified, and we can start designing and analyzing algorithm. So let's do that. And the first and maybe most naive ways to uh, uh, to actually use the very definition of x to the n, a naive algorithm multiplying x to itself repeatedly n times, or to be precise, n minus 1 times, because uh, yeah, multiplying x to itself n times involves only n minus 1 multiplications. So this is one algorithm, and let me refrain from expanding that into some kind of pseudocode. So instead just use this abbreviation, right? As I keep emphasizing, pseudocode is just one out of several possible ways for uh, describing an algorithm. And here's another way of describing an algorithm that computes x to the n by repeatedly multiplying x to itself. And the computational cost incurred by this algorithm obviously is n minus 1, according to our agreed conception of computational cost by counting the multiplications here. And that's the our fourth paradigm, uh, or virtue of computer science, design and analysis. And the fifth virtue asks about the optimality of this algorithm. So do you think this algorithm is optimal, or do you think there's a more efficient way of raising x to the nth power using less than n, asymptotically less? I'm not interested in n minus 2 or n minus 17, but asymptotically less than n multiplication. So again, let's pause for a minute so that you can think about, let me repeat the question. This algorithm for raising x to the nth power by repeatedly multiplying x to itself, is that optimal, having incurring linear cost O of n? Is that asymptotically optimal, or is there a more efficient way? 1 minute pause. And we're back. And to arrive at the answer, let's maybe start by looking at a particular case. Let's try to raise x to, let's say, to the 16th power, or let's say to the 32nd power. Yeah. So x to the 16, yeah, let's say x to the 16 in the naive way would incur 15 multiplications, right? X times x times x, and so on until we've accumulated 16 multiplications of x. So that's this naive algorithm, but there's a more efficient way of raising x to the 16, namely by called repeated squaring. So we first squaring x, that's one operation, then we're at x squared, and then we're squaring x squared itself, thus arriving at x to the fourth. That's the second operation. Second operation, and then we square x to the fourth, arriving at x to the eighth. That's the third multiplication operations of intermediate results, right? So we use intermediate results and multiply intermediate results to obtain x to the eighth in three operation, and another squaring operation, we finally arrive at x to the 16. So this new algorithm, in this particular case, when n is equal to 16, we can get away with 4 multiplications as opposed to the 15 multiplications of the naive algorithm. So it seems that at least in some cases, the naive algorithm is not at all optimal, uh, but we still need to revise our repeated squaring algorithm so that it can cover all possible integers n, and not just those integers n that are powers of 2, like 16. So let's do that. Let's consider a recursive algorithm that computes x to the n recursively by squaring, which is one multiplication operation, by squaring x to the raised to the n over 2, which is well defined if n is even, right? So if n is even, then n over 2 is an integer, and we can make a recursive call. Again, I refrain from uh, spelling out that algorithm as pseudocode, but you can easily express that mathematical equation as a recursive algorithm in cases n is even. If n is odd, then n over 2 is not an integer and cannot be expressed as a recursive call. So in this case, we need another consideration, namely if n is odd, then n minus 1 is even, and n minus 1 over 2 is an integer. So we can make this recursive call, which is now well defined, then incur another multiplication operation, namely squaring, and then perform another uh, multiplication. And you can easily see that this indeed becomes equal to n. This is just applying the usual laws of multiplication and powering, right? So yeah, if you spell that out, this gives rise to x to the n minus 1 over 2 times 2, that's x to the n minus 1, multiplying with x, that's indeed gives x to the n. So that in this way we have covered both cases, n is either even or n is odd, tertium non datur, there is no third case, so that this uh, mathematical notation indicates actually an algorithm that involves only the permitted operation, only multiplications of uh, arguments x or of previous results, namely when we use the squaring operation, that means using a previous result, multiplying uh, previous results is also permitted in the algorithm. Yeah, and as I keep emphasizing, I've refrained from spelling out this recursive algorithm in pseudocode, but we're going to analyze this now. The computational cost, namely the number of multiplications, by setting up a recurrence. And the recurrence is if n is equal to 1, then the number of multiplications used is obviously 0. We don't need to do any multiplications to raise x to the first power. It's just the input is equal to the output. That's the induction start of our recursive algorithm. And more generally, when n is strictly positive, strictly larger than n, then the recursive call makes uh, invokes, uh, yeah, is invoked with n over 2, like in this case, once. Or if n is odd, then is invoked with n minus 1 over 2. So in either case, it's n over 2 rounded down. So here you see the floor brackets. That's a recursive call. And one squaring operation, that is one multiplication of previously computed results, that gives rise to the plus 1 here. And that's all in case n is even. In case n is odd, there's another multiplication by x incurred here. So in case n is odd, this is the more kind of expensive case where we have multiplying the result of the recursive call to itself to express the squaring, and multiplying it with the input x. That's a second multiplication, so that's a case plus 2. So in the case n is even, it's the cost is this plus 1. In case n is odd, it's this plus 2. So in either case, it's at most this plus 2. And this is our recurrence for the analyzing this recursive algorithm from raising x to the nth power. And we can easily solve this right here. You see this here, right? And we can easily solve this recurrence and see by induction that the computational cost, the number of multiplications incurred, is at most 2 times log n. And again, I leave it to you to prove that by induction. It's a nice exercise to practice proofs by induction. But the message here is that now we've designed a second algorithm for solving the powering problem, as we've specified, that now uses not a linear number of multiplications as our naive algorithm here, but this uses an asymptotically logarithmic number of operations. And as you recall from our um, previous slides about asymptotic growth, logarithmic growth is much, much slower, and therefore this algorithm is much, much more efficient than the naive linear time. Okay. So, okay, uh, this illustrates our virtue of computer science. Now the third virtue, design and analysis of algorithm using the previous specification and the semantics with computational cost. And that gives rise now, we will now move on to our first virtue, namely the question whether this algorithm is optimal. So we first designed and analyzed the naive algorithm, asked whether it's optimal, and the answer was no, it's not optimal because we found a more asymptotically more efficient one, which brings us back to square one to the question whether this more efficient algorithm is optimal asymptotically. And mm, so we're now going to give a formal proof that indeed logarithmic number of multiplications is necessary, and therefore any algorithm for solving the powering problem in that way must have incur at least logarithmic cost, which means our algorithm is indeed optimal. So to see that, let us collect some mathematical properties about um, powering. Maybe first we observe that any algorithm in this sense, with this semantics and of primitive operations and computational cost, when it starts with input x, the algorithm, all its intermediate results will be monomials in x, will be powers of x. Um, so That's an important property. And that, of course, makes very explicit use of our semantics, that we only allowed to use multiplications. So any algorithm starting with input x using only multiplication produces as results and as intermediate results only monomials in x, only powers in x. That's straightforward. If you want to prove it, then feel free to perform and prove by induction. That's the first property A. Second property, if any algorithm, yeah, let me emphasize that's very important, that we're arguing about any algorithm. If we want to prove that our algorithm is optimal, we need to make a proof, a statement, and a theorem that takes into account any possible algorithm. So um, that's a kind of framework for the lemma, arguing about any possible algorithm. And here the item B of the lemma says that any algorithm, after having performed L multiplications, well, by item A, we know that the intermediate and the final results will be powers of x, but item B is more explicit about by saying that all the intermediate results are powers whose degree is at most 2 to the L. Okay, so not just are they powers, but here we have a bound on the degree of these powers, bounded in terms of the number of operations performed by the algorithm, namely the number of multiplications. And again, item B is easy to prove by induction. If the algorithm has performed uh, L multiplications so far, then by induction hypothesis, all intermediate results are powers of x with exponent at most uh, uh, 2 to the L. And now we consider another algorithm that may perform um, L plus 1 operations. Then uh, the L plus first operation can at most multiply the intermediate results of degree 2 to the L, and multiplying two intermediate results of degree 2 to the L gives rise to an intermediate result of degree 2 times 2 to the L, which is 2 to the L plus 1, which is our induction claim. Okay, so item B, uh, yeah, I strongly recommend you actually take the opportunity to formally prove items A and B of this lemma by induction, so that you can familiarize yourself with making, formally proving statements about algorithms and optimality of algorithms. So combining the two claims and particularly looking at item B, that means conversely, so since our goal is to compute x to the n to raise x to the nth power, then by this very condition, that means uh, 2 to the L must be at least n, and taking the logarithm of both sides, binary logarithm, means that L must be at least the binary logarithm of n. So um, to conclude, this lemma says that any algorithm for solving the powering problem in this sense, raising x to the nth power, must use at least logarithmically in n many multiplications. And this proves our second algorithm to be optimal, because as you recall, our second algorithm achieves that uh, bound up to a factor of 2. Our second algorithm uses 2 times log n multiplications, and log n multiplications are necessary according to this lemma. So up to this constant factor, which we're ignoring in asymptotic cost analysis, up to this constant factor, actually our second algorithm is optimal, and we have thus uh, kind of solved the powering problem from the perspective of uh, design and analysis of algorithm. We've designed an algorithm solving it, and we have proven it optimal. And now, and only now, we can move on to we should move on to implementing that algorithm and to perform possible optimization. Now that the asymptotic cost has been determined and proven optimal, now Donald Knuth's warning, premature optimization is the root of all evil, um, uh, does not apply anymore because we have already found the asymptotically optimal algorithm, and now we can tend to the constants in the asymptotic uh, big O notation and start optimizing. Okay, so that concludes our um, first example of design and analysis of algorithms with following the um, virtues of computer science. Um, what I like to point out to conclude this slide is, yes, as I said, if exponentiation is permitted, which we did not here, then there's a trivial algorithm that can solve this problem in a constant number, in constant time, using a constant number of operations, namely using the exponentiation operation and the logarithm operation, three operations. But this is, of course, an entirely different algorithmic setting. The difference is in the semantics. The second virtue of computer science specify the semantics of the operations and their semantics. And uh, of course, in our setting, we do not permit exponentiation nor logarithm, but we only permit multiplications. That's first, it's more interesting, and secondly, uh, uh, we, if somebody uh, wants to investigate the problem using or any other problem using exponentiation, he or she will need to boil down that exponentiation operation to single multiplications, and this is what we have considered here. Okay, and now we move on to the second example um, of algorithm design and analysis, the virtues of computer science, namely computing Fibonacci numbers. That's also a very illustrative example. So please recall the definition of the Fibonacci numbers. The zeroth Fibonacci number is 0, the first Fibonacci number is 1, and all subsequent Fibonacci numbers are inductively defined to be the sum of the two previous Fibonacci numbers. Okay, and you know some example of the Fibonacci numbers like 0, 1, 1, 2, 3, 5, and so on. So these are the Fibonacci numbers. And um, right. And an important statement that we're going to prove later is about the asymptotic growth of the Fibonacci number. Namely, they grow very fast. They grow basically exponentially. They grow at least as 2 to the n over 2, as you can easily prove by induction again. And that's important when we now start designing and analyzing several algorithms, actually 5 algorithms, for computing these Fibonacci numbers. Okay, so that's our goal for this slide, designing and analyzing several algorithms. And again, we're going to refrain from spelling out some of the algorithms in pseudocode. So some will be spelled out in pseudocode and some of them won't, because there are many ways of describing algorithms. And so the first, maybe most naive algorithm is just using the mathematical definition of Fibonacci numbers and turn them into a recursive algorithm, right? That's kind of natural because Fibonacci numbers are, after all, defined recursively. So let's convert that into the pseudocode of a recursive algorithm that first considers and covers the two basic cases when n is equal to 0 and when is equal to 1. And then the remaining cases performs recursive calls uh, to n minus 1 and to n minus 2, and then adds these two. Okay. And the correctness of that algorithm is kind of straightforward since it follows the mathematical definition. And the interesting question is, what is the computational cost of this algorithm? And as we've illustrated previously, there are two perspectives of analyzing the computational cost. One is by looking at the bit perspective, how many bit operations are we using? And the other is the perspective of counting, just counting the number of operations. And as we saw previously, the difference between both can be quadratic, but no more than quadratic. So it's up to polynomial perspective. It suffices here that we only count the number of operations and refrain from looking even more closely at the number of bit operations. So how many operations, let's say how many additions of integers does this algorithm incur? Uh, and to answer that question, uh, an important observation is that the number of recursive calls is actually basically equal to the value of the Fibonacci number we are computing. Let me repeat that important observation. So calling recursive Fibonacci calculating algorithm with argument n uh, incurs uh, as many uh, operations as the value of the nth Fibonacci number. Again, this statement is easy to establish using induction, right? As you see here, uh, if if n is equal to 0 or n is equal to 1, then actually the number of operations incurred by this algorithm is at least, here in this case, even strictly greater than the value of the Fibonacci number, which is 0 here. The algorithm incurs a constant number of operations. Here, the second case, also the algorithm incurs a constant number of operations, at least more than one, at least one, which is the value of the Fibonacci number. So this covers our induction start. And in the induction step, um, the algorithm makes a recursive call to this Fibonacci number, which by induction hypothesis incurs cost at least fn minus 1, and makes a recursive call to this Fibonacci number, which by induction hypothesis incurs computational cost at least fn minus 2, and then adds this, which is even more, one more additional operation. So the computational cost of this algorithm is at least uh, the value of the nth Fibonacci number. And this, you might be expecting me to analyze that the cost is at most something, but I keep arguing that the cost is at least something, namely at least the nth Fibonacci number, because as we saw here, the nth Fibonacci number is exponential. That means we've just demonstrated that the computational cost incurred by this algorithm is at least exponential, and I leave it to you to prove that it is actually also at most exponential. So to summarize, that this naive recursive algorithm is actually an exponential time algorithm, which strongly raises the question of whether this is optimal or whether there's a more efficient algorithm. And indeed, there is. And to arrive at this more efficient algorithm, well, let's be clear. You know all these algorithms, right? But the important perspective is now that we're analyzing them. And the point here, observation, is that all these recursive calls keep um, recalculating lower Fibonacci numbers. So make a recursive call with argument n minus 1. If you spell out, if you expand that recursive call will make a recursive call to Fibonacci number with n minus 2. But the previous level also had made a recursive call, so the n minus second Fibonacci number is calculated twice by this algorithm, and the n minus third Fibonacci number is calculated even more frequently, and so lower Fibonacci numbers in this recursive algorithm get recalculated repeatedly, and that strongly suggests that there should be some optimization. And for example, in computer algebra system, when you implement that recursive algorithm and turn on the option which is called remember, which is an option common in computer algebra system, that means that the computer algebra system remembers any previous recursive calls and kind of caches them, and thus saves the cost of repeatedly recalculating the same low Fibonacci number. But if you're not using that option, which is also very memory expensive, it seems like a better idea to devise an algorithm from scratch that by itself avoids recalculating Fibonacci number. And this is our second algorithm for calculating Fibonacci number, now iteratively as opposed to recursively. So this is our iterative algorithm for calculating Fibonacci number. The initial case is treated as here, but now instead of making recursive calls, the algorithm performs a loop, um, and this loop maintains the current and the previous, the last Fibonacci number. So when n is 0, then we're done anyway. When n is 1, then the current, first Fibonacci number is 1, and the last Fibonacci number is 0, the previous one. And now we can uh, iteratively, as in opposed to recursively, climb up the Fibonacci number sequence. Um, so add the last and the current, which we store here in a temporary variable, gives rise to the new current, and the previously current will become the last. So this is kind of a shifting, yeah, climbing along the sequence of Fibonacci numbers. The previously current Fibonacci number becomes the previous one. The formerly previous one is stored here, and then we add these two to get the new current Fibonacci number. That's the idea of this algorithm, and we decrease the count, uh, how far we still need to climb up further by replacing n with n minus 1. So this loop, uh, again, I'll leave it to you to prove by induction. Please do take that opportunity to practice and prove by induction that this is a correct algorithm. Now we really need to do a proof, right? So in the recursive algorithm, it was kind of obvious, but here we really need to prove. It's not difficult, but please go ahead and do prove that this is a correct algorithm, that this does return the nth Fibonacci number. And now our task is to analyze that algorithm. And again, as in previous cases, there are two ways basically of analyzing the computational cost. First, the bit perspective, and secondly, the count the number of operation perspective. And as emphasized before, the difference between both perspective is at most quadratic, is at most polynomial. So let us suffice here that we only count the number of operation. But the important thing here is this is only true because this algorithm only uses additions and not multiplications. So this is a very important property. I'll say more about that in a minute when we talk about the third algorithm. So let's uh, look at which operation this algorithm uses. Well, there are some comparisons, right? There are some assignments. The memory of use of this algorithm is actually very small. It has kind of three variables, right? So, and it uses only addition as arithmetic operation. Only addition is used by this algorithm. And the number of operations is, well, just look at this loop. This loop is executed n times, right? In each uh, iteration of the loop, n gets decreased by 1, and once it reaches 0, the algorithm is done. So that this is a linear time algorithm, right? Uh, the loop body has a constant number of operations, this, one addition, and one subtraction. So, and the loop, so constant cost for each loop execution, and the linear number of it repetitions of that loop. That means it's a linear time algorithm, which, as you recall, is far more efficient than the exponential time algorithm, the recursive algorithm. So we've already drastically improved our computation, our algorithm for computing Fibonacci number from exponential time algorithm to linear time algorithm, right? Or from the bit perspective, it's a quadratic time algorithm if we not count the number of additions, but if we also take into account the length of the numbers involved, the length of the Fibonacci numbers. Um, uh, so to summarize, our iterative algorithm is a linear time algorithm. So, and as you recall from the virtues of computer science, we're now back to square one. So we've designed the first algorithm, analyzed it, asked whether it's optimal, and demonstrated that it's not optimal. Namely, we've designed and analyzed the second algorithm, linear time algorithm, and we asked the question whether this one is optimal. And again, let me pause for a minute and give you time to think. Uh, do you think this linear time algorithm for computing Fibonacci numbers is optimal or not? Pausing for 1 minute. Okay, thank you very much. I've received several very interesting answers to that question, and some people say it's optimal, and some students say there should be a more efficient algorithm. And it turns out you're both right. That sounds like a surprise, right? So that sounds like two different and conflicting answers. Some say linear time is optimal, and others say there's a more efficient algorithm. Some say uh, logarithmic time, and some say even constant time using an explicit formula. Um, yeah, maybe some students have already read the slides ahead, which is fair enough, but which kind of prevents you from thinking by yourself, right? So recall that the purpose of uh, of is to train thinking and not to learn known facts. If you want to uh, learn known facts, then every memory stick can is better. at repeating known facts. But so this is actually, in terms of the Bloom's hierarchy of cognitive learning, uh, being able to repeat known facts is the lowest level, which I'm well aware that you do an awesome job at. But in this lecture, we're actually aiming for the second level, and sometimes even a third, uh, namely being able to analyze. So um, let me uh, let me prove that the iterative algorithm is actually optimal. Any algorithm computing Fibonacci number must have at least linear cost, must incur at least a linear number of operations. So I'm doing that kind of out of uh, to annoy all those who have been reading ahead for the slides and now giving uh, answers that say there's a faster algorithm, because now I want to prove that no, there is no faster algorithm. Any algorithm computing the nth Fibonacci number must incur at least O of n, at least linear cost. And why is that so? Well, look at our bound here on the size of the Fibonacci number. The nth Fibonacci number has a value which is exponential, right? Remember, I asked you to prove that by induction. So since the value is at least exponential, that means the binary length is at least linear, right? So remember that correspondence between value and binary length, right? So an n-bit integer has value at most 2 to the n, and conversely, an integer which has value 2 to the n must have length at least n. So, and since the n Fibonacci number has value at least 2 to the n over 2, it means that it must have binary length at least n over 2. And how does that binary length uh, come into place? How can that even be output? How can we output an integer of length n over 2? Well, that obviously requires at least n over 2 uh, bit operations. So to summarize, any algorithm computing the nth Fibonacci number will incur at least n over 2, that is a linear number of bit operations. And so linear time is best optimal, and this iterative algorithm achieves um, linear time, or quadratic time if we count, uh, move from counting the number of operations to counting the number of, move from counting the number of arithmetic operations to count the number of bit operations. So polynomial time in either case is achieved by the iterative algorithm and is best optimal according to this bound. So we've devised the best algorithm, and um, I know that you're expecting more efficient algorithms because you have read ahead from the slides, but I am going to uh, uh, take and end today's lecture here and explain with a cliffhanger over the weekend, and explain the additional algorithms and their caveats later, and leave it here with this apparent um, uh, 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 paradox that the linear time is optimal, but you have already seen purportedly sublinear time algorithms. So yes, as said, this is deliberately going to take a cliffhanger here, and thank you very much for your attention, and hope to see you again in our next session. Thank you.